Hello, my name is Yamik, and today I'm going to be giving a quick review on the Material Properties FE section for mechanical. If you're looking at your PDF document, it's just pages 98 through 110. And I'm going to start off the review by going over some of the more known items. So in this case, we're going to start off with the Mechanical Properties section. This is stuff we did in our Strength of Materials and Fatigue of Materials courses. And so, you're seeing some familiar items here. So our engineered strain, which is the change in length over the initial length, and then we have the true strain version of that as well. Then we have the engineered stress, which is the force over the cross-sectional area, and then we have the true stress version of that as well. Then alongside that, we have our elastic modulus. Our constant in this is the modulus of elasticity, which is 200 GPa. So you might be wondering what the difference between engineered and true in terms of stress and strain is. And you can tell the difference because the true strain line isn't actually decreasing at any point, and the engineered strain line goes all the way through. So true stresses account for change in the cross-sectional area, while the engineered stress and strains don't account for it. So that's why if you ever see an example like that, you would be able to tell pretty directly based on the true line for both of them never decreasing. Right, from here, we can continue on to the other section we're a little more familiar with, which is the electrical properties section of the material section. So, I know a lot of this is familiar from the applied measurements course that we took. So, in terms of capacitor charge, that's just our capacitance times our voltage. Capacitor from a parallel plate, the epsilon in that represents the permittivity of the material, so that would be provided in the question. Cross-sectional area also being given in terms of dimensions, just multiplying it based on the shape. And the distance between the plates is something that would also have to be provided through the question. The resistivity of a material in a resistor represented by rho, R being the resistance, and A being the cross-sectional area, and then the length also being in terms of most likely millimeters or meters, depending on what the question's asking. So actually, we'll go over a sample question right now. I'll give you guys a little bit to go ahead and pause and resume. If not, I'm going to go ahead and start. So based on what we saw from the previous section, we have our resistance is what we're looking for, and we know we have our equation given the diameter and the length and the temperature. So temperature in this case is actually an extra component. Doesn't really affect the question at all. The only thing it's really affecting is the graph that we're going to use. So like I mentioned, resistance is equal to rho L over A. The rho in this case is the electrical resistivity. So for this question, you would have to look at page 97 in the actual handbook or page 101, depending on if you look at the PDF version, to see the electrical resistivity of copper. So in this case, you go over to the column, you see it is 1.55 times 10 to the negative eighth ohms per meter. So 1.55 times 10 to the minus 8 ohms per meter. And our length in this case is 5 kilometers. Apologies for the handwriting, but that's okay. So, and then we're supposed to convert that down from 1,000 millimeters per meter squared, then 1,000 meters per kilometer. And this is all over our area, and as you see, it's in terms of a diameter. So pi over 4d, which is, my apologies, 2.8 millimeters squared. You do all the solving for this, you should get an answer around 12.6 ohms, and in this case, 13 is our closest option. Let's see what we did there. 13. Perfect. And so this concludes a section of things that we were known directly through our courses. The rest of this is going to be relatively new material. So, all right, now we're going to get into some of that new material I discussed. First thing we're going to learn about is corrosion, and the FE likes to concentrate on corrosion, but in terms of the natural and metallurgical way of it. I guess, we are doing the material science version, so we aren't going to really talk about chemicals, but we're going to talk about the natural version. We have our cathodes and our anodes. The cathodes are the electrodes in which reduction is occurring, and the anode is where oxidation is occurring. So these could be familiar terms from your Gen Chem courses. This is more into a Gen Chem 2 category, but we're going to learn it together. So the corrosion is only possible whenever these two are present, but there also has to be an electrode along with that as well, too. If there's no or if there has to be an electrolyte, excuse me. present in that case as well too. If there's no electrolyte, there's no corrosion occurring. And so it also occurs in like different metal regions. So whenever there's cold work being done near regular temperature or even like a hotter material or metal, there's going to be some corrosion there, and even areas with different oxygen levels too that can really affect your integrity of your metal and make it corrode. So with that, I have an example question right here, and give you guys a second to try it out. All right. So to solve this question, you actually need to use your handbook. So we're going to go ahead and head into our handy dandy handbook right here. So this section's a little bit above the material science section. It's actually within the chemistry and biology section. It has to do with electrochemistry. We can see our aluminum and our copper sections right here. And in this case, you can see that copper has one less electron than aluminum. That would make aluminum the anode in this situation. So if we go back to our PowerPoint, we can see that since in this case the aluminum connector would be the anode, that would make the aluminum connector the corroding one, and the copper would not corrode as a response. So this case B would be the correct answer. All right, we have a second example here too. So you can go ahead and look at this question as well relative to corrosion. All right, and so this one's a bit more general knowledge related, but the correct answer in this case would be A. That being because copper actually has a negative voltage with respect to hydrogen, and all the other three options have a do not have a negative voltage with respect to hydrogen. That's more of something that you kind of have to know within the head, not really provided within the FE handbook, but it's just something to at least realize that copper won't corrode in water, but these other three options will. So now we're getting into the types of failure section of the FE review. There's about 6 different types of failure. The first one we go over is the ductility. So whenever you think of a ductile metal, you should be thinking of things like gold, aluminum, copper, nickel, things that have a large plastic deformation range, as opposed to a brittle material like, say, a cast iron, where it's very, very strong, but it's only going to flake and chip off. It's never going to have any bending to it. Then we have our ultimate tensile strength and our yield strength. So I know we've seen some of these in some of our other courses. So say we draw a quick stress strain graph right here. We're probably a bit more familiar with a graph like this, where we would see at a point right here, we would have our yield strength. And then at this top point portion, we would have our ultimate strength. So the difference is yield strength is the permanent stress deformation, and that's basically the point where no matter what you do with the material, it's going to have some permanent stress related to it. And the ultimate stress is the max amount of stress after that point. So the most stress that the object will endure, so say a paper clip, you keep bending it over and over again. At one point before it breaks, it'll reach its ultimate strength. And then we get to this point at the end over here, which is fracture, which we will get into in the next slide. All right, now we're going to work into the other 3 types of failures involved in material processing. The first one we're going to work with is creep. So creep is more or less a constant fatigue or deformation through an entire process. So the best example I could think of is, say you have a body of water. Body of water is going to be red in this case. And say you have a big block of ice in this water. So I'm going to call this our ice. And the water we can say is 45 degrees. Say our ice is 31 degrees. The water is hotter than the ice. So over time, the ice is going to melt in the water. And so that would be an example of a creep failure. So the ice going from a solid to a liquid would be considered a failure. And that's just because of the temperature differences. It's not anything cyclical like we're going to get into in a second, but it's a constant time-dependent deformation as shown in this equation right here. So the next type of failure would be fatigue. So a good example of this is, say you have a paper clip. That's my rendition of a paper clip. And you bend one end one direction. So say you're bending this one up and down. Say you're bending this one down and up. You keep doing that over time, and eventually the paper clip will break. It'll take roughly 10 to 15 cycles of moving up and down. that would be a fatigue because you are consistently doing a cyclical loading on it, and over time that paperclip will snap. So the difference between creep and fatigue: creep is constantly working, and the fatigue is cyclically loading. And then fracture is what we get into whenever we have cracks in things like, our concretes, our buildings, our bridges, and we're able to actually measure the fracture toughness through this equation mentioned right here. So the geometrical factor would be given in the question, and so would the crack length, and then you'd be able to solve and work around the equation. So now we're going to go ahead and do a types of fatigue example question. So in this question, we can see that we're working with aluminum 2024 T3. We're given the fracture toughness, the yield strength. We're looking for the critical length, but another really key component of this is the fact that we're looking at an exterior crack. So in this case, we're given all the components from the fracture toughness equation as written right here. So y sigma to the power pi a. Now, to work through this question, we do have to go into our handbook. So we will do that right now. And in the handbook, we have our 2024 steel, as mentioned before. And then our exterior crack is, as I mentioned, in this case, y is going to equal 1.1 rather than an interior crack where y would equal 1. So keeping that in mind, we'll work through this question due diligently. So rearranging that fracture toughness equation mentioned before, we're going to be able to develop it to be A equaling fracture toughness over the y, which in this case would be the 1.1 we mentioned from the handbook, and then the sigma y as well as given right here. That would be squared since we're rearranging the equation, and then we'd have 1 over pi. All in all, we go ahead and solve. This is supposed to be k, so this would be 44 over the 1.1, which would be unitless, times 345 squared over 1 pi. You do all the math for this, you should get something around 4.3 millimeters. You want to be careful for the units right here, and this is what you should get as P. Let's see how we did. Perfect. All right, so now we're going to shift gears towards the hardness and cooling sections of the review. So in this case, we're shown that hardness is the resistance from a penetration measurable by a dent. So for example, say we have a piece of steel here. We have our trusty little hammer or mallet, whatever you want to call it. We hit the steel, right? We're going to measure the hardness of this steel by that dent if we have a consistent force on it. And that's where this comes in as well. This diagram right here where we see the centers, the halfway between the surfaces, the 3/4 marks, and the surface overall. And then, so along with that, that'll be key to some of the questions that we look at later. We're going to see this hardenability curve for the steel. So in this case, we have 6 different types of steels marked, and then the distance that they're being quenched, and we'll kind of get more into that in the next slide. So we have the bar cooling rates, where we have bars of metals being cooled in oil, and then bars of metals being cooled in the water as well. So this is all affected by the diameter of the bar, which would be given to you in the question that we would be practicing the FE, and then based off the information here, we'd go back into that hardenability. So we're going to go ahead and do an example right now. Take a second to go ahead and try it on your own, going back to those curves. Both curves shown just now and diagrams were all provided in the handbook, so don't fret, you don't have to worry about them and memorize. So we're going to go ahead. 40 millimeter diameter is given to us. We have a 4140 steel, and we know that it's going to be in an oil bath. And we can see that we're looking directly from the radius and in the center. These are very, very key aspects you need to look at for your material science questions. So with this information, we can go ahead and go back. So we know our bar diameter, and we know that we're going to be looking for the center. So we have our bar diameter in millimeters, center right here. All right, and we know that it's an oil. So we go to the 40 point, we move down to the center, boom, boom. So we're going to see, about 12 millimeters from the quenched end. Given that information, we're going to go ahead and go back to this graph. We knew that we were working with the 4140 steel, and we were, like we mentioned, about 12 millimeters away. Let's go ahead and draw a quick little line. And then we can see that we're looking for the hardness. That's the missing portion of this. And if we estimate it, we can see that this is about, not the best line in the world, but we can see that this is about, 51, 52, 53. I'm going to go in the middle, call it 52, and that should be your answer. All right, now we're going to move on to some composites and ferrous versus non-ferrous materials. At first, I wasn't really aware of what this was, but it's actually quite simple. Ferrous materials are identified as materials that just contain, or materials that contain lots of iron. So, and then non-ferrous is just materials that don't contain that much iron. You can tell, and you can remember this by a little thing. If you remember the periodic table, you'll remember that the iron element sign is Fe, and that's actually due to ferrous and non-ferrous. Moving on from that, we can go into composite materials where we'll have these three equations that seem pretty daunting but really aren't. We're just looking for the density, heat capacity, and the strength parallel to fiber directions. All of these variables will most likely be given in the problem. I haven't really seen an example where they aren't or you have to solve for much. And we can move on from there to an example question. So composite materials are 57% resin, given density, and 43% given carbon fiber and its density as well. And then we are also given the modulus of elasticity at 400 GPa parallel to carbon fibers. Now, one thing we'll notice is none of these really work around the modulus elasticity. So this shouldn't be really needed through the question at all, and we can go ahead and kind of waiver that piece of information. So we're going to be looking for the density, and if we go back and look, we just have our density equation right here, and we can apply that as is. So given rho C equals the sum of Fi, Pi, or rho I, So we can tell that we are given Fi, volume fraction of an individual material, and the density. So we can work from there to go ahead and use rho C equaling 0.57%. And the density of that resin was 2.3 grams per centimeter cubed. And then we have the 0.43, then 1.05. One thing to notice is the units of all of these are in grams per centimeter, so we don't actually have to do any converting. You go ahead and do the math and calculate everything up, you should get 1.76 or roughly 1.8. We can go ahead and check our work. Boom, 1.8. All right, now we're going to get into the main section of material processing FE review, and this is going to be the material structures. So here we have concrete, which is these two graphs are provided in the handbook. So you can see on this first one, we're looking at the water to concrete ratio by weight. And so as you can see, as the ratio becomes more and more proportional, over a 28-day period, the compressive strength becomes lesser and lesser. So you want to be able to find that balance. If you increase your water without increasing your cement mix or concrete mix, there's an overall decrease in the strength. And then you can see this chart over here that's relative to the age in days and the compressive strength. Everything's roughly after 3 days, 7 days, 28 days. And you can see over time there's a pretty exponential difference right about here for the most of them, and then this one up here it takes a little bit more time to flatten out, but over it seems about 28 days they tend to even out. And along with this, we have our amorphous materials. So these are materials that are non-crystalline, not defined in specific atoms. So things that can kind of shift and move around on their own. So we have our polymers, you have gels that can be used in pretty much anything, whether it's consumer care, whether it's machining, and you have our polymers as well. And then here we have our, mentioning polymers, all the different types of polymers and what each individual component can be used for. So in the case of thermoplastics, everything can be melted and reformed. That's one of the qualities. It won't, lose its structural integrity based off of its heat. And then I gave some examples based off of each additive for polymer. So for plasticizers, You have things like vegetable oils, and that's really provided for more flexibility within any material. Some fillers that includes like the particle helps out the particle packing within a polymer. So you can think of things like glass fibers. Really helps out to make sure that you're getting the best product if you have some issues with the particle packing. You have some flame retardants just to make sure you can handle heat better and allow for your polymers not to melt as easily. You'd see this maybe in something like even like a hot glue gun where the entire mechanism is made of plastic and you're melting the heat through a metal tube. So you have the zinc borate and paraffins to help out with that. The ultraviolet resistance, that's really just light dependent. So whenever you're working with light, something like carbon black would be able to help with fading in polymers and issues with that. So this just helps out to ensure that you're going to have polymers that will last a long time and keep their integrity. Oxidation resistance is mainly for corrosion. Even though polymers, you don't really think corrosion over time, if you don't have the correct amount of, in this case, phenols, that will corrode and it won't be a usable product. On to the final section of the material science and properties review, and that is the binary phase diagram section. So this is something we haven't really ran across at all. So it'll take a little bit of getting used to. So we're just going to jump right into it. You see that I have our 4 different reactions right here of eutectic, eutectoid, pertiectic, and pertiectoid reactions. So just to break down this graph, to simplify it, this alpha point and this beta point are both representing solid regions. And then, with the solids, we'll also have liquids. So these L points will represent a total liquid region. The alpha plus the L would be a combined alpha and liquid region, so solid and liquid region. And then the beta plus L will also represent another different solid plus liquid region. Down past this point over here, we recognize that we have a alpha plus beta, which is just a totalitarian solid phase. So in this case, that'd be eutectoid. The eutectic reaction would actually fall in place right about here. So this would be our composition equilibrium, where we have equal amounts of the solids and liquids. So that's where we check off this. And then the eutectoid would come in from our alpha and beta, as mentioned over here. And the peritectic and peritectoid would be the liquid and solid phases. So whenever we have the liquid and solid, we're viewing our composites. So that would be liquid plus solid equaling a solid would be in this lower region, and then the protectoid reaction would be towards the lower region as well too. With that information, we can go ahead and do a practice problem. So in this case, we know that we're looking for the lowest temperature at which the composition is completely melted. So as I mentioned, the eutectoid reaction is the complete liquid reaction. So in this case, whenever we're looking at a eutectic, we're also realizing that is the very beginning of the liquid phase. So in this case, it would be something as of right here where there's that balance between the liquids. And then we don't have that directly, but we can tell through this graph, this is the lowest point of the solids and liquids combined. You can see the line coming through all the way over here. That's representing the solid and liquid break. And this point right here, as mentioned, is the lowest point, or the lowest temperature at which the alloy will become a liquid. So in this case, C would be our answer. With that, this is the end of the video, and I appreciate you for watching.